Hello guys, my name is Zainab Al Kindi, and in this video I will be reviewing a topic which is about hydrogels in agricultural applications in terms of their improving water retention and plant productivity. So let's begin. Nowadays, global need for increased food production due to the rising of global population's demand. However, there is a major limitation for agricultural productivity, which is drought stress. Especially in arid and semi-arid regions, the lack of water can lead to reduced growth, lower yields, and even plant death. To tackle this problem, many years ago, scientists came up with an innovation product which called hydrogels. Hydrogel is a three-dimensional polymer network that absorb and retain water. It stores water during wet periods and releases it during dry conditions. So, there is a need for comprehensive hydrogel research to optimize hydrogel applications in agriculture and also to identify trends and challenges for practical use. So let's start with the types of hydrogel. First, synthetic hydrogels, which are derived from petroleum-based sources. For example, polyacrylamide macroporous hydrogels, sodium acrylamide acrylate copolymer, and potassium polyacrylate. Second, natural polymer hydrogels, which are derived from renewable sources, biodegradable and eco-friendly. For example, cellulose-based hydrogels, which derived from sugarcane bagasse. Also, sodium alginate hydrogels, derived from algae. Also, pectin-based hydrogels, which derived from plant and fruit wastes. Third, hybrid hydrogels, which combine synthetic and natural polymers, for example, dextrine with polyacrylamide, also carboxymethylcellulose with polyvinyl alcohol. Now, let's go through the effects of hydrogels on plant growth from different aspects. First, water retention and drought stress reduction. There is a study done by Baran in 2015. He found an increasing in maximum water capacity in sandy soils and tailings with hydrogels. Also, Al Adrisi study in 2024. He found an enhancement in water retention in treated soil with hydrogel. Second, plant height, biomass, and yield. In 2024, Bulatov did a study and found an increasing in yield of cotton and wheat. Also, Al-Gahtani in 2024, he found an increasing in height, biomass, and root-to-shoot weights of sunflower. Third, root development. Al-Gahtani in 2024 found an improvement of root weight in sunflowers. Whether Ting in 2024, he found that hydrogels reduce shoot-to-root ratios under stress conditions, suggesting water and nutrient localization. According to the soil porosity, aeration, and microbial activity, Zawada and Fudazi in 2023, they found there is an increasing in soil porosity with using macroporous hydrogels. Also, Abdel Ghaffar in 2024, his study found a reduction in soil bulk density. About Ripiro in 2024, he found that there is no negative effects on bacterial growth. In terms of nutrients availability, for example, Shohaj in 2024, he found an increasing in nitrogen and potassium in plant tissues. However, he found a reduction in available phosphorus. As many countries facing the problem of high soil salinity, knowing the performance of hydrogels in saline soil become very important. So, what is the impact of salinity in hydrogels? The studies found that the high salt levels will reduce water absorption in hydrogels. And there was a recent study done by Shen in 2024. He found that the hydrogel capacity in deionized water is about 27.86 gram per gram of hydrogel, and in tap water is about 18.61 gram per gram of hydrogel, and in a solution with sodium chloride 0.9%, it is about 12.22 gram of water per gram of hydrogel. The key reason for that is because the high salt concentration will cause a charge screening effect, shielding hydrophilic groups and reducing swelling. However, there was a recent study done by Ripiro in 2024. He found that cellulose hydrogels can absorb 40 to 50 times their weight in water, even in saline conditions. As many studies done in controlled environment and small scales, there are studies that done in large scale and field. For example, a Ahmedian study in 2024, a research farm of saffron in Iran. The experiment was in 8 square meter plots with 50 saffron corn per square meter under full irrigation and water deficit conditions. The study found that the hydrogel improved plant growth with highest yields at 35 and 50-day irrigation intervals. Also, Zangan and Al-Jabori in 2023, the study was in Sayada Agricultural Research Station in Iraq. The experiment was to cultivate wheat under sufficient irrigation and water stress using a randomized block design. The study found that the hydrogel will enhance the water retention, improve moisture availability, and increase grain yield. What about the biodegradation of these hydrogels? Ripiro in 2024, he tested the biodegradable of the hydrogel. He stimulated degradation using cellulitic enzymes to detect harmful residues, especially epichlorohydrin. The results found that there is no harmful residues were released and no inhibit bacterial growth. Also, at the Satar study in 2024, he buried hydrogel in soil for 120 days to assess the biodegradability. He found that about 96.30% of hydrogel were biodegraded, indicate environmental safety and minimal long-term soil pollution. There is a huge differences between the natural and synthetic hydrogels in terms of cost. For example, the natural hydrogels cost-effective and sustainable because it's made from abundant and low-cost materials, often utilizing agricultural waste like banana, peas, sugarcane, and plant-based polymers. Whether synthetic hydrogels has higher cost because it's typically based on acrylic acid, acrylamide, or similar polymers, which will lead to an environmental concern during disposal. Now, let's go through the limitations and challenges, which are the main things to review such a project. First, environmental concerns with synthetic hydrogels. Hydrogels may cause soil salinization and potential disruption of the soil microbiome. Also, the risk of breaking down into microplastics, which can further harm the soil environment. Second, hydrogel leaching. Some hydrogels may leach from the soil due to electrostatic repulsion with negatively charged soil particles. Another important thing is the research gap. First, soil water characteristics. Only 1 out of 20 studies analyzed the soil water characteristic curves using a moisture pressure plate apparatus. The plant available water is rarely measured despite its importance. The only study that did the soil water characteristic curve is the Zuwada and Fudazi study in 2023. They reported a minor increase in plant available water after adding hydrogels. For example, in sandy soil, it's increased from 30.8 to 30-20%. Whether in sandy loam, it's increased from 27 to 31.6%, indicating a limited impact on soil water characteristic. In addition, the impact on microbial activity. While hydrogels may improve soil conditions and indirectly enhance microbial activity, evidence on the specific effects of different hydrogels on microbial communities is limited. Also, the nutrient availability and uptake. Hydrogels can improve nutrient availability and plant uptake. However, some nutrients like available phosphorus may decrease in soil with hydrogels. So, future studies are required to fully understand these dynamics. Also, the limited long-term assessments. Few studies examine the long-term impact of hydrogel application on soil and plant health, leaving gaps in understanding their sustainability. Finally, the root development. There is a study done by Ting in 2024. They found that there is a restrict root growth, leading to stunted or circular patterns. As you can see here in this picture, the hydrogel's concentration about 0.3%, the roots occur as a cluster of round hydrogel particles. So, the effects of hydrogel composition and application rates on root growth require optimization. At the end, together we can harness innovation to ensure a greener, more sustainable future for agriculture. Thank you for your listening, and I hope this video gave you some knowledge about hydrogel and its limitation on soil science research.